Okay, hello again. This is Tim Hsu from San Jose State University. I'm going to talk today about exponential functions. We'll first start with a definition of the exponential function a to the x. We'll talk about key properties of exponential functions, and we'll talk a little bit at the end about the most awesome exponential function e to the x. Okay, so let's get started. So what is the definition of a to the x? And you'll see in a minute why that's in scare quotes. So just taking a equals 2 as an example, taking our base to be 2, you know what it means to take 2 to the x for when x is a non-negative integer. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. And you also may remember what 2 to the x means for negative integers. For example, well, 2 to the negative 2 is 1 over 2 squared. So since 2 to the 2 is 4, 2 to the negative 2 is 1/4. And similarly for 2 to the negative 1 and 2 to the negative 3. Okay, so what a to the x is, or specifically here, what 2 to the x is, sort of, is that it defines 2 to the x for any real number x in a particular way that kind of connects these dots. In other words, the function a to the x connects the dots coming from the integer powers of x, the powers that we already know. How that's done exactly? Well, take my word for it. It works real well. I guess real talk is that you'd actually have to go through the entirety of calculus to get a really precise idea of what it is. So for now, we'll just sort of take it for granted that this works. Okay. Anyway, more generally, any function of the form f of x equals a to the x, where a is greater than 0, is called an exponential function. Okay. Resuming with our graphing program here, we see here's the plot of 2 to the x, and which indeed connects these dots, just like I said. Here's x equals 1 and y equals 2, x equals 2, y equals 4, x equals 3, y equals 8, 16, 32. And so indeed, the graph of 2 to the x connects those dots nicely. And so to go on to sort of more general a to the x, here are plots of y equals 2 to the x in red and y equals 3 to the x in green. And I just wanted to mention that the characteristics of a to the x for any a greater than 1 is that the graph of that function is going to be increasing, sort of as x increases, y increases, and concave up. So technical meaning of that aside, it sort of looks like part of a smiley face. You can sort of see here, smiley face. The domain of a to the x is all real x, and so no matter what power you take for any real value of x, you can take a to the x. And the range is all y values greater than 0. You only ever get positive values. In fact, it's a little harder to see, but you actually get all possible positive values. So the y-intercept of any function y equals a to the x is y equals 1, and there's no x-intercept. And again, as x gets really big and negative, as x goes to negative infinity, y goes to 0. Oh yeah, and the one other thing, the reason I have 2 of these functions up here, is that if you have a larger a, so here's larger a equals 3, and a smaller a equals 2. So the larger a is the faster y increases as x goes to plus infinity and decreases as x goes to negative infinity. So here's just a question for thought, or you can find this in the book if you look carefully enough. So if a is less than 1, all these things up here are depending on a greater than 1. But if a is less than 1, what does the graph of a to the x look like? How does this change? Try thinking about what happens when a equals 1/2 or 1/3. All right, so at this point, we should mention that there is one exponential function that is better than all the others, namely f of x equals e to the x. Well, you may ask, what do I mean by e? Where e is a number that looks a little something like 2.71828, and so on. It doesn't keep repeating 1828. There's more interesting stuff from there, but it's kind of neat that you have that repetition right away. Or if you really want to know something about what e is, it's the limit as n goes to infinity of 1 plus 1 over n to the n. Well, that clears it up, right? Okay, that's not particularly useful either, but at least I've sort of specified what e is. Anyway, the point is, the reason that e to the x is interesting is, well, you'll have to take my word for it at the moment. The point is later we'll see that e to the x is important because its calculus properties are more natural than the properties of other exponential functions. And that's why if we ever refer to the exponential function, we're really referring to e to the x. Okay, so enough wasting time on the internet. Go do something useful. Thanks, bye!